yeah, so this exponent nu is, of course, known from, say, Nikolai Prokofiev simulation. That's the number I'm quoting here for O to n equals 2. So all the numbers are n equals 2, correct? Oh, yes, it does. So, there's rough agreement, but the best values are from Monte Carlo. So if you want anything to any precision, the only method is Monte Carlo. But the whole point is Monte Carlo is in imaginary time, and I can't do it in real time. There's a sign problem, and so I can't use Monte Carlo to get the low frequency behavior. But I can match it to the high frequency behavior in Matsubara space. Okay, so that's, so the OPE has gone us part way, and it agrees beautifully with Monte Carlo, so it's got us part of the way. And this is a language just built upon these operator product expansion. Okay, so finally, I'm going to change gears a bit in a way and do holography. So let me give you a kind of a map in the 15 minutes that I'm going to spend to explain what's here. Okay, so this was the old-fashioned way where we identified quasi-particles and used the Boltzmann equation. Now we have taken these two steps in a new way, where we make no reference to quasi-particles, but only to primary operators and OPE coefficients. And we find this only gives us the conductivity at high frequencies. It can work at finite temperature, but frequency is bigger than temperature. Now we want to go to low frequencies. So at this point, there is no there is no method that's fully under control. But for certain class of models, which are invariably matrix models, these are models of matrices of n by n matrices where n goes to infinity, and if you want exact solution, they also have to be supersymmetric. We can actually go further. So what we're going to do here is make those same steps for models which are not large n matrices, but they do give us a physical, at least a somewhat uncontrolled, but a systematic way of extending to low frequencies. I mean, in a sense, you could also say that the Boltzmann equation is an uncontrolled extrapolation to low frequencies. It works extremely well, though, but it's not systematic. It's an infinite summation. And so we're here, of course, things are much more primitive, but so we're just making the first steps in learning how to control this large step. So what's going to happen is that we're going to relate these OPE parameters, the CFT data, to a theory of gravity on anti-de Sitter space in one higher dimension. And then that theory of gravity will acquire a horizon at a Hawking temperature T, and from the dynamics of that horizon, we'll be able to obtain the low frequency extrapolation of the CFT. So that's the big picture. It's a program that we're trying to implement, and we've just made the first steps. But at this point, we'll be the first to admit that it's not there's no small expansion parameter. It's just something that works. We know this whole procedure is exact for certain matrix models, and we're just going to apply it here. Okay, so first, let me give you a quick derivation of where this anti-de Sitter space comes from, and how one should think about this extra dimension, and why is there a theory of gravity. So the conventional way of thinking about conformal field theories or fixed points of field theories is a renormalization group, which tells you that you have some coupling constants in your field theory that change as a function of energy scale. And one of the key properties of the renormalization group is that the right-hand side doesn't depend on u. It doesn't depend on the scale at which you're measuring the coupling. You can just keep doing it again. So that's the beta function. So there's some sense in which the physics is local in u. You can do a transformation from one length scale to the other, and things look kind of local. All right, so here's a kind of a pictorial definition of RG. You start out with some system on a lattice, a boson's moving on this lattice, and then you rescale. And this is the short distance or high energy scale, and this is the low energy or long distance scale. And you get some effective couplings, and the entire history of the RG is shown here of some models. Okay, so, and now I'm going to just replace u by r. So that'll be r equals 0 will be high energies, r equals infinity will be very low energies. So the whole idea of the ADS-CFT correspondence, roughly speaking, this is only for you to have a mental picture, is to interpret this extra dimension as another dimension of space-time. So we're going to map a theory that lives on the boundary to a theory that lives in one extra dimension with its emergent direction r, and we should view r as the length scale at which you're exploring the theory. Okay, so let's just first imagine that this is possible. Once you accept that, then you can very quickly see that the only possibility for the metric on this space is anti-de Sitter. And that comes from this very simple argument. So this conformal field theory in the boundary has the property that it's scale invariant. So you scale x and t by factor zeta. And let's imagine, so the physics should be invariant under the scale transformation. The theory of gravity, which has proper distance ds in the extra space-time, is invariant. So ds goes to z. So now you simply ask for a metric which is conformally invariant under x and t, or in fact just Lorentz invariant in the xt plane, and then also has this property. Well, there's really essentially only one metric up to reparameterization invariance, and that's this one. So you can see now if I take r go to zeta r, that r is the emergent direction, then this is true, very trivially. It's obviously Lorentz invariant because it's minus dt squared plus dx squared. And so you can only multiply this thing by functions of r, and there's only one function of r which will obey this. Up to this, okay, there's some reparameterization invariance that you can use to show that this is unique. And this metric is the metric of a maximally symmetric states. In the case of d equals 2, is anti-de Sitter 4. Yes?
I thought that you use the translation symmetry, the Poincare group and dilatation.
That's all I used. That's right.
Not all conformal group.
Correct. So that's the point I'm just going to make. Yes.
So that's saying that there is no metric which preserves dilatation and translation doesn't preserve conformal.
No, so far I've only used translations and, Poincare group and dilatations.
But this has a full conformal symmetry.
Yes, so the anti-de Sitter 4 has a full conformal symmetry. Correct, it does.
So that means there is nothing in between. I cannot find a metric which preserves.
Yeah, so this means that, if I think I understand what you're saying, scale invariance implies conformal invariance. I've implicitly assumed that is true for the class of theories for which this mapping works, correct. But there may be other theories which are, nobody's found really clear-cut examples, but there's no proof. I'm certainly assuming here, for anything that I'm interested in, it's true. So the point I was going to make is right here. So this very simple argument used only Poincare and scale invariance, but you get a metric which actually has a much larger symmetry. ADS4 has a very large group of isometries. I forgot, SO4, 2 or something like that. And it turns out, and this is at this point looks like a remarkable coincidence, the group of isometries of ADS4 is the same as the group of conformal transformation in 3 dimensions. And this holds in any dimensions too. And that's the seeming coincidence that's being exploited. So the theory on ADS4 has a full conformal symmetry, as does the boundary theory. Okay, so that's just at a very general level. Now it turns out that this ADS4 is also the solution to the very simplest and the original theory of gravity, and that's the Einstein theory. It's one of the solutions where you take a negative cosmological constant. Okay, and that the scale, so in the combination of the gravitational constant and the cosmological constant will give you one dimensionless number, and that dimensionless number is related to what's called the central charge of the conformal field theory. Okay, so now you have 2 theories. One is a theory with gravity. I guess I haven't proven that, but I just assume that. Living in ADS4 and a conformal field theory living on the boundary, and those in some sense describe the same Hilbert space. That's the claim of the correspondence of, I should have said Maldacena and many others. Now you can also relate correlations of one theory to the other by something called the Gupser-Klebanov-Polikov-Witten ansatz. which says the following. So here's your CFT with some operators OA sub x, and you insert some sources phi of x. So once you're able to evaluate this for the CFT, you know all the correlation functions of this OA sub a sub x. It turns out that these correlation functions are equal to the partition function in ADS4. This is, partition function in bulk. So this is the bulk theory, S bulk, of some theory of gravity with the following constraint, that the fields have to, up to some powers of r, have to be equal to the sources that you put on the boundary. So there's a boundary, you fix the boundary values of the theory in the bulk, and those boundary values of the sources conjugate to the operators of the CFT. So that's, so for every field, so what this shows you is that for every field that lives in the bulk, there's an operator of the CFT. And you can, by just taking derivatives, you can get multi-point correlation functions. You can relate correlation functions in the bulk as they approach the boundary to correlation functions of CFT. And this is somewhat like the LSZ reduction formula of field theory, where you're relating correlators to S matrix elements, and this here, the S matrix elements are the correlators of the CFT. Now, there are two other, so as I said before, there are two very special operators for CFTs, the current and the stress energy tensor. And they have very special properties under this, this mapping too. So the currents, it turns out, all map to a gauge field. So for every current, there's a gauge field. So there's a U1 conserved current, and there's a U1 gauge field, A mu. And so that you can now postulate an action, F squared, with a coupling constant G. And I'll say without proof, this coupling constant G is then this number sigma of infinity. That's exactly the number that came the 2-point correlation function of the current. Then the other special quantity is the stress energy tensor, and there's a similar relationship for that. And the stress energy tensor is conjugate to variations in the metric. So fluctuations in the metric, which this is why you have to have a theory of gravity, the fluctuations in the metric correspond to correlators of the stress energy tensor. So the very simplest possible theory that you could take as representing a conformal field theory on the boundary is the Einstein-Maxwell theory. You take Einstein electromagnetism and, Maxwell electromagnetism and Einstein gravity, which is really quite remarkable, in 4 dimensions, which is exactly the dimensions Einstein and Maxwell worked in. So this is characterized as by 2 dimensionless numbers. The GM is a dimensionless number, like the fine structure constant, and the combination of the Newton's gravitational constant and the cosmological constant is a dimensionless number. And those 2 dimensionless numbers correspond to the central charge of this conformal field theory and this number sigma of infinity, the high frequency conductivity, in the classical gravity approximation. Okay, so what we've seen is that this Einstein-Maxwell theory can at least reproduce the 2-point correlation functions of the current and the stress energy tensor. In fact, it reproduces automatically and much more easily from many points of view the full tensor structure of these correlators, which is rather complicated in general dimension. All the constraints from conformal invariance come automatically. But how about the OPE? So remember, I looked at the OPE of 2Js that had many terms. So you want to match that too. So we're going to match the OPE. So the idea is that every OPE gets matched to some classical theory of gravity. And you have to actually add a few more terms. This is what took us a few years to figure out. To match the yes.
So the O2 symmetry you have.
Yeah.
Is identified as a U1 symmetry.
Yeah. O2 U1 the same. Yes, correct.
And then in the bulk is a gauge U1.
That's correct. That's correct. Yes. Any other questions? All right. So this you may remember this constant gamma. I'm sure you don't. So this constant gamma was one of those things in the OPE, which seemed rather mysterious. 4 minutes. Okay, I'm almost done. Hard to believe, but true. And here it corresponds to the simplest 4 derivative term you can write down, which couples the Weyl tensor to the electromagnetic tensor.
What's the Weyl tensor?
It's some variation of the Riemann tensor. It has the property that it vanishes on anti-de Sitter space, some function of the metric.
But it vanishes in this
In pure anti-de Sitter, yes.
fluctuations. These are fluctuations.
But at finite temperature, it will be important. Okay, and then there was this thermal operator O with scaling dimension 3 minus 1 over nu. You got to add another field conjugate to that we call var phi. The mass of that field becomes the scaling dimension 3 minus 1 over nu, and this coupling constant alpha is related to an OPE coefficient. So basically, in fact, in some ways more simply than you could do in the conformal field theory directly, just by writing down things that are general coordinate invariants and using other symmetries, you just take some general theory of gravity, you see what kind of conformal correlation functions it applies, and you automatically satisfy all the conformal Ward identities. And you also get to know how many free parameters you have, at least at the level of classical gravity. Of course, all these parameters, in the end, the value of alpha, gm, and m squared, and gamma are some numbers that you can determine by Monte Carlo simulation if you worked hard enough. Okay, so finally, what use is all this? So why am I doing all this? So far, I've just shown you that there's a machine for generating correlative functions of a conformal field theory that may be a bit simpler than the machines you knew before, but it's giving the same information. So where things become really interesting and totally new is you now turn on a temperature. And now it turns out this same action, the Einstein action, has a whole family of solutions for the same parameters. I just showed you one of them. And the family of solutions are characterized, and I'm sorry, there's two different R's. This capital R has nothing to do with the Riemann tensor. With the horizon at a distance r from the boundary where the conformal field theory is living. So if I heat up, and what does this horizon correspond to? Well, if you take a conformal field theory at a finite temperature T, associated with that I can define a length scale r. And so there's a horizon at that length scale r. And that horizon will have a temperature whose Hawking temperature, since it's the horizon of a black hole, or really a black brane because it's infinite in space. And the Hawking temperature of this horizon is the temperature of the conformal field theory. And finally, you have this very beautiful correspondence that dissipative properties, if you look at correlations like, and this can all be done in real time. You don't have to do this in Euclidean time. If you apply the Kubo formula, determine the conductivity here on the boundary, you can relate that to the damping of waves going across the horizon of a black hole. So those numbers there then relate back to the conductivity. So that's what you do. You now have a theory of gravity. You take it to finite temperature. You fixed all the numbers by the OPE in principle, and you compute the conductivity. So after many years of work, that's our result. So there's a combination of numerical gravity in the presence of a black brane and OPE info from the quantum Monte Carlo. And then we have the full frequency dependent of the conductivity. Okay, this part fit to the OPE, and then everything else comes from the gravitational theory. So at this point, we don't know how reliable this is. We're continuing to work and looking at how robust this whole prediction is. Absolutely, it's the real part that's harder, and the real part is the dissipative part. Sure, you can just take a Kramers coordinate. We have, in fact, the conductivity of the entire complex plane. We also know its poles in the lower half of the complex plane, which are so-called quasi-normal modes. So we have the kind of information. It's so rich that you rarely get it by any other. Even the Boltzmann method, those things are hard to get. Anyway, so just to compare, this was the Boltzmann solution. Looked very different, and this thing diverged. It then goes to infinity. And this is there's an amazing connection, it seems. They're all computing the same thing. This is a solution from solving dynamics of a black brane with coupling constants given from the operator product expansion. Okay, so that's my conclusion then. Not all systems have quasi-particles. In fact, some of the most interesting ones don't. And these are systems where you can't braid them, you can't write down a Boltzmann equation, you can't do all of that. You really have to use a whole new set of ideas. And for conformal field theories anyway, there's the right object, it turns out, it seems like if I really want to force in some understanding of what the normal modes or what the degrees of freedom are, they're strangely enough associated with the normal modes of a black brain. Okay, thank you.
Okay, I think we have time for one or two questions.
Yeah.
Yeah, I just wanted to say whether you can comment on one thing, since you mentioned black hole inside a book. So I heard some story just recent, maybe some time ago, say, for example, in MIT group,
Yeah.
trying to consider non-Fermi liquid
Yeah.
On the boundary with a charged black hole.
Yeah, sure. Or
Yes, hole, right?
yeah.
The story I heard is something like because the black hole entropy was not fully considered at that time,
Yeah.
and the non-Fermi liquid behavior is associated with that entropy in certain way. So if one takes into account for that, maybe the non-Fermi liquid will become Fermi liquid. Is there some?
Yeah, so there is a very long story there. And there was, Hong Liu and John's very important early work. And there's been a lot of work since then, including by us. And I think, yeah, so I don't know if maybe in private discussion I can tell you more, but let me try to summarize. Yes, it's true that you can take some of these metallic states and equate them conjecturally to a charged black hole, not a neutral black hole that I discussed here. And there are very nice charged black holes which match perfectly the entropy, specific heat, and also the entanglement entropy of the boundary theory, and also obey the right type of exponent inequalities. The original proposals didn't quite do it, but now there are improved solutions.
Somehow I heard a story saying only, for example, like this super young mirrors without black hole, that's only that case will be non-Fermi liquid. If you have a black hole,
Okay.
something like
I don't think there's any such statement. I mean, I think there are no exact results there. Even for super Yang Mills, we don't know what happens at finite chemical potential. So things are very much more, it's another subject. We should talk about it. But I of course, it's very close to my heart, but it's not what I talked about.
Okay, that's time to be again.
it's the pointer. You can use mine if you want. Thanks. Thank you.